University Complutense of Madrid, and then a Master's in Physics and Technology Nuclear Reactors at the University of Birmingham. And I'm currently doing a project on the linking of subchannel analysis tools with advanced multi-scale core simulations here at the University of Liverpool. So to start with, what is nuclear power? Nuclear power is an advanced source of energy generated in nuclear reactions such as fission, where in general heavy nuclei are broken into products by neutrons. Roughly 200 megaelectron volts of energy are released in the form of kinetic energy, where neutrons emitted allow to sustain a fission chain reaction. As seen here, where for this case, the fission reaction for 235 uranium is shown, where the neutron is absorbed by the uranium to form an unstable nucleus, which then splits into several fragments as well as other neutrons. In thermal reactors, neutrons are slowed down to increase the fission probability, with most of the world existing commercial reactors being thermal reactors, such as Magnos, AGR, PWR, BWR, RBMK, and BVR, as well as CANDU. So, as the main type of nuclear reactor being treated in this project are pressurized water reactors, the main elements are described, these being the reactor vessel, which is conformed by fuel assemblies which are submerged into the moderator coolant, with each fuel assembly being conformed by fuel rods as well as control rods. Each fuel rod is composed by the fuel used to produce energy, it being 235 uranium, and the clad used to contain the fuel as well as exchange heat, which are all of which are contained in the reactor core. Each control rod is used to control the fission chain reaction, with these being made out of boron. And finally, the coolant is used to remove the heat generated in the nuclear reactor. Where other elements of the actual nuclear reactor include the pressurizer used to keep the reactor at the right pressure, the steam generator used to exchange heat between the primary coolant circuit and the secondary coolant circuit, as well as the turbine and the generator used to convert mechanical and thermal energy into electricity, and the condenser, which is used to cool down the coolant in the secondary coolant circuit, which is then pumped back into the steam generator. So why use nuclear power? Nuclear power allows to answer the energy demand in the energy demands here in the UK, as it does not depend on weather conditions, which is of vital importance for the UK due to its unstable weather conditions, and it does not produce CO2 emissions, which adheres to the zero CO2 emissions policy of the UK. So, reactor core analysis consists on the interaction between power production, which is studied through the subject of neutronics, where a derivation of the Boltzmann equation known as the neutron transport equation is solved, and heat transfer, which is studied through the subject of thermal hydraulics, where the fluid dynamics equations known as the Navier-Stokes equations, as well as the Fourier law, Newton's law of cooling, are solved. Nuclear simulation software allows detailed calculations of both the neutronics and the thermal hydraulics of nuclear reactors, which allow to improve their economics and safety. State-of-the-art nuclear simulation software allows a good balance between the demands of the nuclear regulator, the industry, and the rest of the community, including the university. With some examples of LWRs, including the Consortium for Advanced Simulation of Light Water Reactors, as well as the Nuclear Reactor Simulator. Neurasim, which are both based on coupling different codes to obtain improved results. Neurasim does not offer high fidelity results, while CASO requires high computational power, it not being currently applicable in the UK under current industry constraints. So an intermediate multi-scale software development is proposed to answer the demands as well as operate under reasonable computational power. Here on this graph, it can actually be seen that this software development aims to have a higher scientific novelty than Neurasim, but still be able to answer the current industrial demands more than CASL. So it aims to answer the demands by overcoming conservative designs to basically improve the economics and safety, by developing a system architecture for code coupling, which allows to improve communication between the different functions of the reactor core, and with coupling extending to high fidelity information, again to improve their economics and safety, and integrating the code into a user-friendly software framework to reduce human errors. It aims to operate under reasonable computational power by solving the neutronics and the thermohydraulics at the pin level of the hottest fuel assemblies only, while still solving the rest of the reactor on average, so that high fidelity results are only focused where required. Here we can actually see the whole of the reactor core being treated using a nodal method, while in particular hot fuel assemblies, as seen here, are treated at the pin level. So currently, the linking of subchannel analysis tools with advanced multi-scale core simulations is of concern, and hence work is focused on thermohydraulics. Tasks performed include a thermohydraulics literature review, a 4 days Panther nodal method code training course at EDF, as well as a TTF study and latter application to the benchmark for evaluation and validation of reactor simulations, as well as to the OECD PWR subchannel and bundle tests benchmark. So now I'm going to talk about the code that I've been using, which is CTF subchannel analysis code. So Coolant 2 Fluid is a thermohydraulics code developed by Pacific Northwest Laboratories, which uses a 2-fluid, so liquid and vapor, 3-field liquid drop, liquid film, vapor approach, where conservation laws are applied, these being known as the flow field equations. Both PWRs and BWRs can be modeled at the pin level using mesh cells, which together can form subchannels, with different subchannels being connected in between through gaps to form a section of the reactor core, generally consisting on the active length of the fuel assembly. Here we can actually see a mesh cell characterized by its cross section, its node length, as well as its width. Where here we can actually see different mesh cells all piled up to conform a subchannel. So, now I'm going to talk about the benchmark to which CTF has been applied quite recently, as opposed to the previous one, which was already explained in the conference in June. The OECD PWR subchannel bundle tests benchmark is an experimentally and computationally validated benchmark, where experimental data has been provided by NUPEC using a test in Japan using a test fuel assembly, and code results have been provided by more than 20 academic and industrial participants. This benchmark is divided into a void distribution as well as a DMB benchmarks, as these magnitudes are of vital importance in when analyzing safety in reactor core analysis. As for example, the void distribution affects the reactivity through the feedback void coefficient, which basically, when it was positive, it gave rise to the Chernobyl accident by increasing the criticality, while the DMB affects the criticality, the structural integrity of the clad. In particular, for certain test series, we can actually see the the radial geometry as well as the axial geometry with the different pressure spaces, grids, and which are the cause of the pressure losses within the fuel assembly. The radial power distribution for the different subchannels within the fuel assembly, as well as the axial power distribution. So moving into the results, simulation of the void distribution benchmark includes 43 subchannel and 35 bundle tests that have been performed according to hot fuel assembly conditions. Where here we can actually observe the temperature of the coolant